Today we are determining the internal forces as a fraction of x. Another alternative of studying the internal forces variation in a structural member is to express the internal force as a mathematical fraction of the longitudinal dimension x. Thus, the axial force, shear force, and the bending moment of the section are expressed as px, vx, and mx respectively, where x is the distance measured along the primary dimensions from one of the members, e.g. 4.12. For the course, we will consider the left end of the member as the origin unless otherwise specified. Note that equations involving these internal forces change if the direction of the positive x or its origin changes. So here is our beam. We're having a pin and the roller. The origin x is equal to 0. So if we cut a section at a distance x, vx, since it is on the right, our shear force would be facing up. The axial force will face on the left, on the right, and then the bending moment will face to the anti-clockwise direction. So the internal forces are distance x from the origin. Considering an example, 4.6 again, we shall cut a section at C at a distance x from A, 2 kilonewtons, 1.5, that's the reaction. This was our AY and AX. Then cutting our section x at a distance x from A, we shall have the axial force facing up, the axial force facing the left, the shear force facing up, and then the bending moment facing the right or the anti-clockwise direction. What happens is that if we consider another section at a distance x, but a distance beyond the 2.5 load acting on the beam, our axial force will face up. Our axial force will face on the right, the shear force up, and then the bending moment anti-clockwise, as seen in the figure B. Then figure C, we cut at a distance x beyond the load 3 kilonewtons. These are our free body diagrams up to the distance x from the origin. Now, for x equals 0 up to x, so between x less or equal to x, 0 less or equal to x, 0, between 0 to 6 for the distance x, our general formula for the internal forces and the moments, we will take the summations, shall consider the equilibrium conditions, summation of the forces in the y direction, in the x direction, and then the bending moment at the point where it was cut, shall have mx minus 1.5 times x equaling to 0. When x is 0, the bending moment is 0. When x is 6, our bending moment becomes 9. Then similarly, we can find out the internal forces in the position x equaling to 6, equaling to 10 meters, x equaling to 12 meters, so depending on the figure. So between 6 and 10, between 6 and 10 meters for the x, shall take the equilibrium conditions, summation of the forces in the x, summation of the forces in the y, and then bending moment z. Our bending moment mx plus 2 into x minus 6, that's the horizontal distance. The perpendicular distance minus 1.5 times x. Then now, when x is 6, the bending moment becomes 9, and when x is 10 meters, the bending moment becomes 7 kilonewton. Then between 10 and 12, still taking the equilibrium conditions, our bending moment when x is 10 is going to be 7 kilonewtons, and when x is 12 it becomes 0. Then from there we can draw our axial, shear and bending moment diagrams depending on sign convention. Sign convention for P is negative 12. For the shear force, it's negative and then positive. Then the bending moment is maximum at 9 kilonewtons. So that's how we determine the internal forces at a given distance x.